appreciate the visual feedback. However, if you can turn your microphones off, that would be really helpful so that we don't get any sorts of feedback. But first of all, I will hand you over to Professor Andrew Cruden. Thanks very much.
Okay, thank you, Jenny. Just to give a bit of an introduction and overview of this EPSRC CDT in energy storage and its applications, and it's that key bit at the back, looking at applications of energy storage as well as some of the main technologies that hopefully will come across in this quite mixed range of presentations earlier. So the CDT started with its first intake, and we had 5 annual intakes starting in October 2014. So according to my maths, we took in our last intake on October 2018. So we recruited a total of 53 students, of which 21 have now graduated. And again, some of the work that you'll see just now is our students coming towards the end of their studies and now starting to write up and present. Again, the vision for that CDT, as most CDTs, was to train future research leaders within this field. So again, it is in specific technologies and how you apply those technologies. And clearly energy storage is a very active area covering everything from grid, transport, consumer goods, and even probably increasingly looking at elements of thermal storage as we look to try and address the issue of the stopping of gas boilers, for example, in new homes. In fact, and not many years away from now, actually, that's going to impact us. So again, there's clearly an awful lot of interest in this field. Again, if we take a step back and look nationally, there's an awful lot of activity in this field. Again, a lot of it seems to be based around about batteries. For example, the UK will have 2 gigaplants quite soon, one in the Midlands and one up near Blyth. So again, there's an awful lot of activity in this field. But again, as I say, this particular CDT was covering a range of energy storage technologies, and I'm delighted that the talks today will cover, again, a suitable mix of those type of technologies, everything from mechanical systems, i.e. flywheels. We've got batteries, we have flow cells, again, we've got elements of technology relating to thermal storage, and we've also got economics as well, because you can have the best technology, but if it's far too expensive, then that seriously hinders its application. So without further ado, I would like to hand over to Andy Hutchinson, who will give us our first talk. Thank you very much, Andy.
Thanks, Andy. I'll just share my screen now. Hopefully everyone can see that, I assume?
Yes.
Yeah, perfect. Okie doke. Right, hi, I'm going to be giving a talk today on using Flywheel energy storage to enhance generation and distribution installations. That's a slightly different title to the title I originally gave, but I was very ill with the flu when I gave that title, so I didn't have much time to think. But it's generally the same kind of thing. Okay, so first I'll give a bit of an outline on what I'm going to be talking about. So I'll touch on what Flywheel energy storage is, and then discuss what the key question that I'm trying to answer with this research is. Pull out some research highlights from different papers that I've published over the past 3 years, and then discuss a few conclusions. So Flywheel energy storage, it's a type of mechanical energy storage where electrical energy is converted into rotational kinetic energy and stored until required. These on the left are the flywheels that I've been working with my industrial sponsor on, small modular ones. They're short duration, but they've also got a high self-discharge rate, so they tend to discharge their energy quite quickly if they're just left to run. You have to keep topping them up with extra charge. And they're ideal for highly cycle-intensive short-term storage applications. So high power, low energy applications are where flywheels are most effective. Key question that I'm looking to answer is, how do we exploit these characteristics that I've just mentioned to improve the performance of both proposed systems and existing systems? A couple of example applications where this could be exploited. These are things that I've touched on across my research over the years. So Wind generation sites where you've got second-to-second fluctuation. You might have grid level curtailment or local export limitation issues. And they're also obviously rapidly increasing in deployment where you've got more and more renewable penetration across most grids across the world. Frequency response services where you might be trying to maintain the frequency at a certain level depending on the country. These often have very high cycle rates, so a lot of energy throughput, and there are a vast number of battery energy storage systems already deployed that provide this service, including Willenhall, which is a battery energy storage system owned by the University of Sheffield that provides frequency response services intermittently. And for this application, both power and energy are important. You kind of need the energy storage to last over the days and weeks and months, but you also get paid based on how much power you're providing. So you need a balance with that application. And also ramp rate management. Sometimes you might have a traditional generation application where it's a diesel generator or it's a gas turbine, which might take time to ramp up, and that rapid increase in power can be compensated for by a flywheel, where your flywheel starts off at full power, and as the generator ramps up, the flywheel decreases its power output as the generator increases its power output. And this is a good application for a flywheel because power is the main requirement. It's only needed for a short duration. You don't need to store that energy for a long time. You can just keep it spinning at a certain level. So onto the model. So at the top of the screen there, you'll see an excerpt from my battery model in MATLAB and Simulink. The flywheel model looks very, very similar. It's just got different mechanisms for self-discharge and different values for various things, but broadly it's made out of very simple building blocks, which mean that it can be applied to lots of different applications really easily, really quickly. And that means that it's really flexible in what I can research. There's less groundwork in building models when you can just plug and play different pieces. Bottom left there is a comparison of real-world battery data taken from Willenhall and comparing it to my model performing the identical power output taken from Willenhall. And you can see there that in orange is the model state of charge as it follows that same power output. And in blue, which you can barely see because it's behind the orange, is the recorded state of charge at Willenhall. And this was just to verify that the model is operating, you know, like a real world battery. And I've got a paper coming out very shortly that talks more about how we've verified that, but that's a good explanation of the verification work done behind it. And then bottom right, you can see operational graphs from the model. So this is a flywheel providing dynamic frequency response service. You can see the frequency fluctuating at the top, and then the flywheel providing power. The flywheel state of charge changes according to how much power it's delivering at any one point, and then the cycles are steadily going up as it's operating. So this is all just to show the fundamentals of the model that we then use to assess different applications. So one of the applications I've looked at is hybridizing frequency response services. So I said before, there's a vast amount of already deployed battery energy storage systems across the country. We've taken a baseline of a 1 megawatt hour battery providing a dynamic frequency response service 24/7, and then introduced a small flywheel into that system to try and take some of the strain off the battery. So on the baseline, the battery was experiencing around 6.8% degradation per year, which is obviously quite a significant amount of degradation and could easily lead to that affecting the economics of the site. Whereas we then looked at 3 different control schemes for how a hybrid system could be controlled to minimize that degradation. And control scheme 1, where you've got the flywheel and the battery energy storage operating in tandem, but the flywheel is acting as a filter to any request. So the flywheel tries to take control of it first, and if it can't fulfill the request, it passes it on to the battery. And that actually reduced the degradation over the year down to about 2%. So it's a significant degradation saving, and that can lead to excellent economic benefits. We did a net present value study on this, which showed that you could achieve positive net present value for quite a wide range of flywheel sizes. Other application we looked at was if you wanted to do dynamic frequency response with only a flywheel, so no battery involved at all. And we looked at these configurations here on the right in the table 1. And the Oxtow flywheel is probably the closest to configuration F in terms of its makeup. And we looked at what cost, total capital cost per kilowatt it would take for each one of these configurations to have a positive net present value. So for it to be economically viable, how cheap do you have to make it? And the answer is very. This study kind of showed that the flywheel can't handle this task on its own. For that configuration F, which is a 15C flywheel providing a 1 megawatt service, you would have to get it down to around £220 per kilowatt, which is just not feasible. But it does provide that target there, that if you want the flywheel to do this service on its own, that's what you need to be aiming for in terms of total capital cost. And then the last application I'll touch on is wind curtailment support. So this was a wind generation site in Northern Ireland where the site could generate up to 500 kilowatts at any one time, but local distribution conditions meant that they were restricted to 250 kilowatts. So we looked at different sizes of energy storage system, flywheels and batteries to try and absorb any of that power that's generated above 250 kilowatts and then supplement it when it drops below that to try and capture some of that wasted wind energy that they're currently being restricted to. And you can see here, figure 6 and 7 at the bottom, these are 2 different operational scenarios. So looking at 2 different ways in which the site manages how and when it cuts out the power. And you can see in both of those, the flywheel configuration A and B, which is the purple and blue ones, could lead to quite a significant amount of extra income over the course of 20 years. Under operational scenario 2, that was peaking at around £200,000 over the course of 20 years. And we also did net present value studies on this. And again, the flywheels provided positive net present values for different targeted outputs of the site. So if you were targeting 250 instead of 230 kilowatts, then you could get a lot more value out of your system. And this kind of shows that in this scenario, flywheels are perfect for it because it's very power intensive. There's not a huge amount of energy throughput. It's constantly charging and discharging. So the cycle resilience that they have is really important. Whereas the batteries, they're getting exposed to so many cycles that they can't really keep up with it and they degrade too quickly and therefore aren't economically viable. So in summary, I've talked about how flywheels have to be used to their strengths. Trying to use them for energy intensive applications results in poor economic performance generally, but power applications is where they shine. Coupling them with batteries in some scenarios can result in a more profitable and higher performing installation when it can minimize the degradation being affected by that battery. And in other scenarios, a flywheel can perform better than a battery on its own, mainly when the cycles are very intensive and the energy requirement is low. I've published quite a few papers on the subject so far, so please contact me if you would like to read any further on the topics I've touched on, or feel free to email me with any questions. Thank you very much.
Andy, that's great. Thank you very much. Almost bang on time, so thank you. Again, if we can just reiterate Jenny's request, any questions to Andy, you can just put them in the chat and hopefully Andy can respond while the next speaker is on. So again, moving swiftly on, can I now ask Harriet Kimpton to present? Again, this is again another different strand for energy storage with a focus more on thermal storage. So over to you, Harriet. Thank you.
Okay, thank you. Can you hear me? Let me just get my screen up. Hello?
Yes, we can hear you. Yes.
Can hear me. Let's see if I can. Can you see my presentation?
We can indeed, yes.
Yep.
Yeah, perfect. Thank
you. Right. Okay, perfect. Right. Today I'm going to be talking about a brief project overview of my project, which was looking at using silver nanofluids for solar connectors, which are connected to a thermal storage system. Firstly, I'm going to give a brief introduction and then I'm going to look at some of my methods and results and then look at some conclusions and outlook and finally finish with acknowledgements. So firstly, to start with, as you all know, we've got to try and look for a low carbon method of producing heating and hot water. So one option might be to use an enhanced solar thermal collector and connect that to an interseasonal energy storage. But firstly, you've got to answer two questions. Do you need to enhance the efficiency of your solar collector? Can you store the energy in a reasonable space? And what type of interseasonal energy storage would be best? So to answer those questions, at the start of my project, I did a short paper looking at the feasibility of this, and enhanced capture efficiency is beneficial. Of the three types, thermochemical energy storage is the most suitable, and this on this side of the page shows you a little bit about what thermochemical energy storage is. It's where you use a reaction to be able to separate two components and then store one of the components at room temperature, or if you have to, store both of the components at room temperature and then recombine to give you your heat back again. But a thermochemical energy storage, you still has to be fairly large, and the whole system would only be feasible as a standalone if you got less than the median demand for heating and hot water, greater than the UK average roof area of 15 meters squared, and enough space to put a big store. And also further significant research is needed, both around the integration of the collector with the thermal store and the nature of the thermochemical energy store itself. But I'm going to focus on enhanced solar capture. Here we've got a schematic of two types of solar collectors. This is a standard surface absorber solar collector, flat plate collector, which has an efficiency of about 46%. And this is a schematic of a direct absorption solar collector with a nanofluid flowing through it, which, because it used volumetric absorption and less copper and stuff like that, there's potential for an efficiency of improvement up to say 50 to 80%. If you can improve the properties of your nanofluid further, you could maybe further improve that. For example, you could use silver, which produces a large but narrow absorption peak, which can then be tailored by changing the silver nanoparticle geometry. And that is going to be the focus of my thesis, with the aim of investigating silver and different morphologies of silver nanoparticles, and also of protecting the surface of the silver with a coating to see and then measure its performance and stability under application relevant conditions, to look to see if this sort of thing could be commercially viable. Right, so what methods did I use? Well, to start with, I looked to develop a broadband silver nanofluid by combining a number of, well, in this case, 3 different shapes of silver nanoparticle together, and then to measure the performance and stability using UV vis spectrometry and a solar simulator, and then also to look at what's happening with the morphology by using TEM. And this is a graphical abstract for one of the papers that I have published on this, which shows sort of adding the reagents and coming up with the 3 different nanofluids, which can then be combined to give you your broadband absorber. And then I did some further work and I demonstrated that you could get a possible photo conversion efficiency for this broadband absorber of about 85%. And here you can see this is the UV-Vis spectra, and that's one of the nanofluids, that's another of the nanofluids, and that's the last of the nanofluids, and the black line here is the broadband absorber. And when you combine them together, the performance of the broadband absorber is a lot better than its components, and especially much better than water. Okay, but, and this is a big but, they're not morphologically stable to either temperature or with simulated sunlight. So what can you do about it? Well, I decided to look at doing a coating on the silver nanoparticle, a silicon oxide, which is a transparent coating. I used a wet chemical method, which is described here. So you take the silver nanoparticle, you silver nitrate, you make your silver nanoparticle here, you then protect the surface of that, and then you add the tetraether orthosilicate in a basic ethanoic solution, and you end up with a coating of silica oxide on the silver. Okay, and then I assessed its performance and stability to see if there was any improvement by doing this compared with the uncoated silver nanoparticles. And I managed to produce a consistent coating method, which coated with a 50 nanometer thick silica oxide coating onto the silver. And here you can see a little silver nanoprism, which has got a coating around it, and this is the silver nanoprism on its own. I then measured the performance and the stability of the nanofluid, comparing the 3 together, and you've got the and what this showed you was that it wasn't improved by coating with the silica oxide. Right, so I was able to develop a novel broadband silver nanofluid with potentially enhanced solar performance, but the sunlight and elevated temperature morphology stability was an issue. I was able to develop an optimizer coating method, but it's not a suitable means of enhancing stability. So the commercialization of these sort of collectors based on silver as a nanofluid would be very, very challenging. And really, in the future, to aid decarbonisation, I think the focus should really shift into other methods, so of improving solar thermal uptake, like making them cheaper, making them cheaper and integrated with systems, and also looking at further research into the thermochemical storage, because that bit needs to be sorted out. There's no point in improving the efficiency of your solar thermal collector if you're only using it for hot water. So there we go. I'd just like to acknowledge the University of Southampton and this CDT for their support for this. Thank you very much. Any questions?
Thank you very much, Harriet. That was very interesting. Again, just in light with the other speakers, any questions to Harriet could ask, if you can put them in the chat just now, please, and hopefully Harriet can respond directly. Again, there might be time at the end to have any direct questions. So thank you very much, Harriet. Can you stop sharing your screen, please? And can I, in the same breath, invite Dermot Roberts to make his presentation, which again is going to be about economics, but of lithium-ion and flow cells. So over to you, Dermot.
Thanks, Andy. If I just share my slides, can you confirm that you can see them? Oops, 1 second.
I can, yeah, if you can put them in presentation mode. Yeah, perfect, thank you.
Great. All right, thank you. So, yeah, my name's Dermot. I've actually come to the end of my PhD just about, because I submitted it in October and I'm just waiting for the Viva in March. So today I'm going to talk about a kind of case study from the last chapter of my PhD, which was about comparing vanadium flow batteries with lithium-ion batteries for supporting solar power, so firm solar power in California. So I'll give a quick introduction to the vanadium flow battery, because there's a chance some people haven't heard of this before. It's essentially another type of battery. The key feature of it really is that you store your energy in liquid in tanks in the form of vanadium in different oxidation states. And when you want to charge or discharge the battery, you pump this liquid through a electrochemical reactor. It's really quite similar to a fuel cell. And yeah, the benefits of this have been claimed. First of all, you've decoupled your power and your energy rating. So you can essentially have whatever duration of battery that you want. There's no degradation of the energy store. So the actual electrolyte, it's just a solution of ions. So there's not really much that can go wrong with it. And even if something happens and it precipitates, you can still recover the vanadium in the future. So that's a benefit from both a cost perspective potentially, but also from a sustainability perspective. The vanadium flow battery has reasonable efficiency, so it's probably going to be somewhere like 75–80% efficiency round trip, which is slightly less than a lithium-ion battery, which is probably over 90%, but it's way better than something like hydrogen storage, which is probably about 40%. The downsides of the vanadium flow battery are that it has low energy density, which means it's probably more suited to large-scale stationary storage, although people are actually talking about using them in canal boats in Europe, because the good thing about it is you can actually just pump fresh electrolyte in when you want to charge it. And if it's on a boat, the weight isn't actually that big an issue, because you need ballast on your boat anyway to keep it upright. The other downside is you have a higher cost per kilowatt. So the electrochemical reactor here is actually quite expensive. So you're unlikely to install, say, a 1 hour duration vanadium flow battery, because it just wouldn't compete with, say, lithium-ion batteries or even flywheels like Andy was talking about. But once you get out to maybe 4 or 5, 6 hours duration and beyond, it's probably quite competitive. At longer durations, maybe not so much. You might end up being better with something like hydrogen, because the storage cost of hydrogen is ultimately lower than the cost of vanadium. I hope that makes sense. So the case study that I'm going to focus on today, like I said, it's providing firm power from PV. So firm power essentially means you take an intermittent renewable power and you use some kind of storage device, say a battery, to be able to take the surplus and deploy it when it, at night time when it's a deficit. So you're getting something that's a bit more like a traditional power plant that can match supply and demand. Now, doing this with PV is ideal for batteries, because you really only need 4, 5, 6, 7 hours of duration, which a battery can easily handle. It's not like storing wind power in the UK, where you need potentially weeks of storage duration, which would be really expensive with batteries. California is an ideal location, additionally, because it's sunny, simple as that. I was trying to think of a case study where vanadium flow batteries are actually likely to be deployed and compare it with lithium-ion batteries in that setting, as opposed to some setting where neither of them are actually going to be that economically viable. So the question I want to answer is, which of these two batteries can give a lower cost of electricity over a 20-year project? The other thing to point out is on the right here, this is the daily kind of load profile for the site that I'm looking at. So I'm looking at behind the meter installation of a battery, as opposed to putting the battery at some really large scale standalone solar plant. So here, this is actually a grocery store in California. The nice thing about this site is that the power consumption of the grocery store is correlated with PV output. So you get higher power consumption in the summer. So that's August is labeled there in the graph. And I think that's mainly due to loads that are related to cooling, so air conditioning and also probably refrigerating your produce. So that's already makes it a good case study, because if your renewable output is anti-correlated at a seasonal level to your demand, you're going to have real problems meeting or becoming self-sufficient. Okay, so the first thing I had to do was work out or model the costs of each of these battery systems. So when people talk about lithium-ion batteries, for example, reaching a cost of $100 per kilowatt hour, this doesn't necessarily apply to stationary storage, because with stationary storage, you've got all these additional costs like the balance of system hardware. This is this BOSH here. So that's things like cabling, inverters, all the other kind of control system that you need to operate your battery. And then you have EPC, which is engineering, procurement and construction. So you have to put your battery somewhere. Chances are you're going to have to build a kind of concrete plinth to put it on so that it doesn't get flooded or suffer any other issues. So these costs kind of add up. And if you look at the graph on the right for the lithium-ion battery, you can see that even when you get to quite long durations, like an 8-hour, 12-hour system, only about 50% of the total cost of the energy storage is actually the lithium-ion cells. And it's the same for the flow battery. The only difference is with the flow battery, you have a kind of distinction between power costs and energy costs. And you can see that for the flow battery on the left here, as you increase the duration, the power costs fall quite considerably. So that's the kind of dark purple series at the bottom. But the energy cost stays the same because that's the cost of your vanadium, which is proportional to the duration of hours of storage that you have. Overall, at short durations, the lithium-ion battery is definitely cheaper, but at longer durations, they're actually very similar. Now, when I started out doing this research, the kind of received wisdom that was that the vanadium battery would become cheaper after about 4 hours duration, but that's just not the case anymore because the cost of lithium-ion cells has fallen so much in the last 4 years that I've been doing the work. So really, they're very similar in terms of upfront costs. Okay, so the first study I did was for each of the battery technologies, find a combination of photovoltaic array size and battery size, both power and energy rating, that gives the lowest levelized cost of electricity at different levels of self-sufficiency. So a kind of feature of renewable-based grids is that if you want to become very highly self-sufficient or have very high renewable penetration, the cost starts kind of escalating. So you can see that in this first plot here. So on the x-axis is the self-sufficiency ratio. So it's how much of the power demand on site is being met by the battery and the solar panels. And on the y-axis is the levelized cost of electricity, which is essentially the average cost of a unit of electricity produced by the system across the project life. And you can see as you go up past about 90% self-sufficiency, it starts to accelerate. And I didn't actually go up to 100% here, but it's getting steeper and steeper. This is looking at the vanadium battery for comparison, and I've overlaid the two here on the right. Now, in my base scenario, the flow battery comes out cheaper slightly. I mean, they're quite similar, really. You have to remember that the battery only makes up part of the cost. The other part of the cost is the photovoltaics. The other thing is that if you want to get really high self-sufficiency ratios, you really need to oversize your photovoltaics. So you can see here, I went up to, I think, about 180%. So as in you size the PV so that it could provide 180% of the actual demand. So that's what you have to do to cover the periods where there's just low PV output. The battery itself isn't enough.
Dermot, that's 10 minutes.
Okay, no problem. I'll try and go through those last bit quickly. One of the other things I realized as I was doing this is that if you're not careful with the lithium-ion battery, you find that the state of charge drifts up in the summer, because essentially the algorithm just says charge the battery if there's surplus PV. So you have a big battery in some situations and it charges up, but it doesn't fully discharge. So you can see here that your minimum state of charge, it's never actually emptying. Now this is bad for the lifetime of the lithium-ion battery. So I developed a kind of sub-algorithm to push down the state of charge by not overcharging it if you don't have to, which involves a bit of forecasting. And what happens then is that at the kind of higher self-sufficiency ratios, the cost of the lithium-ion is then pushed down. So you actually end up being cheaper than the flow battery at high self-sufficiency ratios, but not so much at low self-sufficiency ratios. Okay, so conclusions are the vanadium flow battery and lithium-ion battery give a similar levelized cost of electricity, which it's actually I thought was actually surprisingly cheap. So getting up to about 95% self-sufficiency at around 20 cents per kilowatt hour. The flow battery is likely to be slightly cheaper at self-sufficiency less than 90%, but above this, the meter battery has to do as many cycles, which favors lithium-ion because when it has high cycles, it degrades. And the other thing is state of charge management is important for the lithium-ion economics. So thanks for listening. We've actually, currently just making some edits to a paper on this, which has been resubmitted. So hopefully that will be published soon if anyone wants to take a look at it. Thanks for listening.
Okay, thanks, Dermot. Again, if there are any questions for Dermot, can you put them in the chat? Hopefully he can address them directly. So thank you. Now, our next speaker, Flora. Flora is on the call, but is going to be using a recorded presentation. Is that correct, Flora?
No, so I'm not going to be doing a recording. I'm just going to do it live.
Excellent.
Which is probably good news because I can make it shorter so that we can all finish on time.
Okay, no problem. Well, anyway, sorry. So I'll hand over to Flora. Thank you.
Okay. Right. So I'm just going to attempt to do a screen share. Can someone confirm that you can see my screen?
Yeah, that's fine, Flora. Yeah.
Okay, perfect. So today I'm just going to give a brief summary of some of the work that I've looked at throughout my PhD. And in the interest of time, I'm going to try and make this very brief. Fortunately, there's quite a lot of overlap with some of the previous talks. So I won't go into too much detail on kind of background and theory. So my PhD is relating to optimizing the economics of energy storage. So I'm going to start by sort of explaining my motivation behind this, then kind of go into what questions I'm specifically addressing, how I've been addressing them, and if I've got time at the end, then I'm going to give you guys a bit of an exclusive preview of some of the results that I'm going to be showing at our upcoming CDT conference. So as we've seen, energy storage can bring value in lots of different situations for a variety of different users. Now in my projects, I'm particularly interested in how commercial and residential consumers can use energy storage to reduce their bills and to generate revenue. So the questions that I've been looking at are firstly what markets and what mechanisms we can use to generate revenue. So how can we use energy storage to make money, essentially? Secondly, I've looked at some locational factors that are going to affect the economics, and I'll explain this in a bit more detail later. And finally, I've been addressing kind of uncertainties in predicting the revenue generation. And just to note that throughout this, I've been looking at both batteries, primarily lithium ion, and also hydrogen. Okay, so onto mechanisms for revenue generation. So here are a few of the mechanisms I've been looking at in my PhD. So firstly, arbitrage. Now this is essentially purchasing electricity when prices are low, using it to charge up your battery, and then at a later time when prices are high, discharging your battery and selling the electricity for profit. I've also looked at ancillary services, which are a collection of services that National Grid uses to balance supply and demand on a second-by-second basis and keep the frequency of the grid at 50 hertz. So these are generally procured through monthly auction markets. So as an energy storage owner, you can participate in these markets by placing a bid which may or may not get accepted. So I've looked at how we can optimize the bidding strategy in order to have a bid that's accepted, but also at a favorable price. And finally, I've looked at co-locating energy storage with renewables. So this is all about the kind of trade-off between selling the renewable power directly versus using that power with energy storage, such as a battery or an electrolyzer, and then discharging your battery when prices are more favorable, or selling on the hydrogen. And kind of the trade-offs between these two and whether or not we can generate value by incorporating energy storage. So on that last point, when we're considering co-locating storage with renewables, there are some locational factors that we need to consider. And this is actually something that's not been looked at too much in the literature. Now, clearly, when we're talking about renewables, not all sites are created equal. So some sites are going to have greater natural solar and wind resources. And additionally, in Great Britain, the electrical grid is split up into different distribution grids, which all have their own time-varying use of system charges. So depending on whereabouts you are in the network, you might experience different charges. And this is also going to affect the economics that you can achieve. And so practically speaking, if we're looking to deploy energy storage, it's something that's worth considering. And finally, kind of local constraints. So looking at grid supply points and whether or not there is headroom for additional capacity. And the final thing I've looked at is addressing uncertainties in revenue generation. So here are just a couple of things that can cause uncertainties. So we can't perfectly predict what the market price is going to be like or the discount rate. And additionally, there may be future improvements in the technologies that are going to affect CapEx and efficiency. So we need ways to kind of incorporate these uncertainties in our economic calculations. So I've used a variety of methodologies to address these questions. Primarily, I've been developing optimization models in different scenarios, which effectively schedule your energy storage. So when your battery charges and discharges to maximize profits. I've also used classifiers with the auction markets that use historic data to kind of train the classifiers. And then we create some hypothetical bids and see whether or not they get accepted or rejected and use this to kind of optimize the bidding strategy. I've also used geospatial analysis, which is basically mapping, and using it to kind of locate some of the optimum locations to deploy energy storage. And finally, I've looked at something called real options analysis, which is a financial tool for decision making under uncertainty. So just to finish with some results, so I'm going to be presenting these at our upcoming CDT conference, and these are from a case study where I've taken a wind farm and I've looked at co-locating an electrolyzer and also a battery there, and seeing whether or not that adds value, or in the case of purple on this graph here, whether there's losses due to the high capex of these technologies. So what I'm showing here in green are the scenarios where value is generated by incorporating energy storage. So what we can see here is when we've got large electrolyzers, small batteries due to the high capex of batteries, meaning that the economics generally aren't great. The PPA refers to the export price, so the price that our wind farm owner gets for directly selling the wind. So when this is low, it's favourable to use the wind power to generate hydrogen and sell it on. And so it follows that it makes sense that we have a more favourable outcome when hydrogen price is higher. And I've also looked at, with the same model, how incorporating energy storage can reduce the curtailment of the wind site. So on this graph on the left, we've got the percentage of curtailed wind that gets used by the storage. So when there's no storage, that's 0. And as we increase the size of the battery and increase the size of the electrolyzer, we can use more of this curtailed wind. And what I'm showing here is the optimized scheduling of the electrolyzer and the battery. So the dark blue shows the export of power. The sort of pale green shows wind self-consumption, and the white areas show curtailed wind. The red is the initial wind generation, and you can see with these hashes here when the electrolyzer is using the wind power, and these dotted regions when the battery is using it. So that's just to kind of show you one example of one of the models that I've looked at in my PhD. If anybody's interested in finding out more about this, then I'll be presenting this in a lot more detail in the CDT conference. And if you've got any other questions, then please do get in touch after this. So that's everything that I wanted to talk about today. Hopefully, I haven't gone on for too long.
No, Flora, that was spot on. Thank you very much.
Right, stop sharing.
Okay, so again, just to summarise, we're slightly over time. Again, I think some of the speakers might be able to stay on if anyone has any direct calls. I must admit I haven't seen many questions in the chat, but hopefully, again, our speakers can pick them up and respond directly if that's doable. Again, just to bring this to a close, again, thank you very much to UKCRIC for offering us the chance as the energy storage and its application CDT to present. And again, many thanks to our 5 speakers who gave their time to, again, just talk about their specific work. And again, just put it in context, the range of opportunities that are being explored and the range of technologies within the energy storage sector. So, Jenny, I think I'm drying up now. I don't know if you want to say anything just to conclude this.
Thank you very much. I just wanted to say thank you to everyone who's attended today. As Flora mentioned a couple of times in her seminar, her webinar presentation there is a multi-CDT conference coming up on Tuesday the 5th and Wednesday the 6th of April, hosted by the University of Sheffield. There's details about that on the UKCRIC Skills Network web page, and I'll also add a link to it in our thank you email. It's free to PGRs to attend this conference. You just need to sign up through the CDT ESA website. I would love to see a number of you there. We look forward to kind of hearing from Flora and from her other colleagues some exciting results from their current research. So I just want to round up by saying thank you very much to everybody who presented, to Andy and to Tracy as well for helping me organise this event. And we look forward to seeing you at future UKCRIC events. If you have any feedback or you want to mention anything that you'd like to see at a future event, then feel free to drop me an email or pop it in today's chat, which will stay available for a while. But other than that, I will let you all get along. So thank you very much.
Great stuff. Thank you. All the best.
Thank you.